we have introduced the heuristic solution method to solve TSP, which serves as a building block for today's lecture. So now let's talk about how can we solve VRP problem with fast algorithm. So different from a traditional TSP, VRP is much more complicated because we may incorporate the capacity issue of the trucks. And also we need to divide the customer into multiple groups. So both of these features significantly increase the difficulty to solve the problem. So there are many ways we can introduce heuristic solution. But now let's talk about an interesting algorithm which is based on a two-step method. So the core idea behind the two-step method is pretty simple. So that is, we need to convert the problem into a customer grouping problem. After the customer is grouped, then for each group of customer, we just solve a typical TSP. So let's see how can we achieve this. If we have a depot and several customers, consider a simple example where we only have 2 trucks. So an immediate intuition is, can we just group customers into 2 subgroups, and then we're just using one truck for one group and then another truck for another group. So we need to balance the travel distance of each truck and also the capacity of the truck given on the demand. That is to say, if we have some customers which have huge demand, the number of customers should be less. If we have multiple customers with very small demand, we tend to group all of them together. Because these 2 decisions are twisted, so it's not easy to directly address any of them. That's why we need to introduce a heuristic. So let's try to estimate transportation cost for customer grouping. So one immediate idea we can imagine, we want to aggregate customers into groups. Let's pick up one point as somewhat our center of the group. And then if we have a depot which is far away from the center, then we can try to estimate a region where all the customers are nearby the centers. So our truck will depart from the depot to our center and then travel some distance and serve all those customers and then go back. So under this intuition, we tend to group those customers which is close to the center, but also we need to incorporate the distance to the depot. So to achieve this, we define a closeness measure for each customer to a customer center and then the depot. So we'll try to evaluate the distance from the depot to the customer center and to customer center to a certain customer, and then from the customer going back to the depot. Definitely we can travel a different direction from the depot to the customer or customer to the center and the center back to the depot. So we insert this customer to this group with these customer centers. We can evaluate how close this customer to the group of customers. Therefore, we can define a measure where the center we denote it by m. So it can be the depot index is 0. So the travel distance is from depot to the customer center plus the center to this point, and then from this point back to the depot. Definitely, we can have another direction from the depot to the customer, from the customer to the center, and from the center back to the depot. We just evaluate the minimum value of these 2 costs to indicate the tour distance. And also, we want to consider the impact of the distance from the depot to the center by minus depot to the center plus the center to the depot. So after introduce this measure, we can immediately see a trend. Let's see, this is a depot. This is our customer center. And then there's another customer I and a customer J. From the measure we just defined, the distance from depot to I to center will be smaller than the distance from depot to J to center. So that means we intend that if we want to group this customer to the centers, our preference is customers I, not customer J. In this end, we kind of measure the distance from customer to a center. So let's see if we have depot, and then we have two customer centers, and then we have customer I and j. Then our measure can differentiate customer I to customer j. If we go this direction, our measure can provide a closeness from I to M1 definitely is smaller than j to M1. And also we can have j to M2 is smaller than j to M1. So based on the closeness measure, we can easily differentiate which customer preferred to allocate it to which centers. So in this case, customer I has a higher chance to be grouped to center M1, and customer J has a higher chance to group to center M2. So after we have multiple centers, our goal is trying to allocate those customers which has closest distance to each center. For example, we can allocate this customer I to center M1 because the closeness to center M1 is definitely smaller than it is to M2, it is to M3, and it is to M4. Then we try to allocate the customer to the center M1. So similarly, for those customers near M2, near M3, near M4, we try to group all the customers with their centers, because for those customers, their closeness to the center nearby is smaller than those two other centers. Okay, with this distance closeness measure, we can have intuition about how should we group customers because they are close to the centers. But definitely there's another issue, which is the capacity. So for example, if we have the depot and the center, if we have a lot of customers around this center M1, but we only have two customers around center M2, then one possibility is that the total demand near center M1, this demand can be too big. So under this case, although those customers are close to center M1, but we still need to detour some of the customers to center M2 because the capacity issue. So to this end, we need to provide a customer assignment measure that can help guarantee that the customer within each group do not have the demand oversee the capacity. So to achieve this goal, we will introduce a method called flow assignment with minimum cost. So this is a very famous problem in graph theory. So consider that we have a bunch of centers. Let's see if we have M trucks, then definitely we will have M centers. And then our goal is to try to allocate those customers. Each customers have their own demand. And then for each center, we want to allocate some customers to the centers. And then such that the total demand, definitely the center has its own demand. Then we want to guarantee that the total demand is smaller or equal to the capacity. So in that sense, we can create a demand called V minus D1 at center 1. And then if this demand can be consumed by customers on the right-hand side, let's see if V minus D1 is consumed by D2 plus D3 plus D4, and then we can have the demand D1 plus D2 plus D4 equals to the capacity. So in this sense, we will solve a flow assignment problem where for each centers, we have a capacity minus this demand to be the rest demand to be consumed by the customers on the right-hand side, which are all other customers. And then, remember we have this closeness measure. Allocate those customers with smaller distance or smaller closeness. So that means we can have some cost terms on this assignment. So finally, if we can find an assignment solution, then for each centers, we can have a group of customers. And then the total cost of this assignment is minimized. This is called the flow assignment problem with minimum cost. So let's now summarize our two-step method. So the first step, we try to calculate the closeness from customer I to center M. And then based on this closeness, Step 2, we solve a flow assignment problem such that for a center we allocate a bunch of customers where their closeness, the total cost is minimized. So that means the closer of the customer to the centers, the better we can allocate the customer to that center. And then the capacity V is guaranteed. And then after we finish the assignment problem, then we have our grouping. After the customers are grouped, then we can solve TSP within each group.